Good morning.
Good morning, sir.
Let me know if my screen is visible.
Yes, sir. Visible, sir.
Yes, nice. So we have talked about the two types of loaders in the previous classes, that is absolute loader and bootstrap loader. So bootstrap loader, let me revisit once again. If you have any doubts, let me know. Okay. So bootstrap loader, if you look at the definition, bootstrap loader is a special absolute loader. These are the two adjectives what we have to use, because these two are specific to bootstrap loader. So bootstrap loader is a special and an absolute loader whose responsibility is to load the operating system whenever the system is switched on. That is the reason why I would say the system is booting. So what is happening at the stage of booting? The bootstrap loader loads the operating system into main memory. So we have seen that why it is required and all, but that is the concept or the functionality of a bootstrap loader. So once that is done, its duty is over and it will not be doing anything else. So that is the concept of a bootstrap loader. Now let us see the absolute loader concept as well. So absolute loader is the one that makes sure that it loads the entire program at the address that is specified as part of the object program. Okay, so now bootstrap loader is a absolute loader, meaning that the bootstrap loader always confirms that the operating system is loaded at a designated location. So thereby, in our bootstrap loader of SICXC as well, we are going to consider certain assumptions just to understand how the program is going to be written. This is very important from exam point of view. In exam, they might be asking for 8 to 10 marks. Explain or write the algorithm for a SICXC bootstrap loader. So you should understand the concept what we have seen yesterday, and that is going to be helpful for you. You cannot try to by heart this. You should be able to understand the flow of logic behind this. So to start with, we assume that bootstrap loader itself is loaded at the location 0, whereas operating system is loaded from the location 80. So if that is the case, the bootstrap loader that takes the operating system from secondary memory has to load the operating system from the location 80. And you know that all the addresses are in the hexadecimal form. So to start with, we have two parts of the program. So first part is to take the character, convert into its internal representation, later store that into the memory. So two parts means taking the character is the one part, later converting that into its internal representation is the other part. So here first let us see about the first program. So this is a program what is there in the book. I want to show some differences what I've taken yesterday. So in the book it is given as what? 128. So I have written yesterday as a 80. So don't waste your time in converting 128 from decimal to hexadecimal and all headaches. So that is the reason why I have written in the previous class as a #80H. I cautioned you to not to forget writing H. So don't write 128 and all. Don't waste your time. As it is, you write LDX #80H. So that is the difference what I want to show from the yesterday what we have taken and what is there in the book. So both are same. Normally the numbers are given in decimal here. Later we have to convert into hexadecimal. So what is the number we are supposed to store? 80. So why you have to invest your time in understanding 80, 128 and all to make your concept understanding easier? I replace this with a #80H straight away, so that you will not have any confusion between the address and the program. Okay, so that is the first thing what we have to note. Now the first part here is how to convert the given character into internal representation. So clear A, accumulator is cleared, because you know accumulator is used for almost all types of activities, especially data transfer and the arithmetic and logic operation. So we have to make sure that accumulator is free from any existing data. Now LDX, why? Because index register, because every time we need to start loading the data from location 80, so we need to increment the location X. So that's why LDX we have taken. This is a hash 80H. We can write that straight away. Now we'll take a character. So we get, see, there is a subroutine. We get the character. We'll see how it is being done. Once that character is taken, so get C will store the character by default in the accumulator. And we know that object code is given as a nibble form. That is two characters supposed to be part of one byte or one character set, but that has been given as a two independent characters. So we need to convert them into internal representation. So the first part what I have taken now, the first character of a 1 byte will be stored into the special register called as a S, which is a general purpose for us now. Later that will be left shifted by 4. Why it left shift by 4? Because in a 8-bit arrangement, first character is what having a higher order, second character will be having a lower order. So 3 has to be always in the higher order. So from lower order, we have to shift towards the left so that becomes a higher order. That's what normally we do in the digital electronics. Okay, higher order and the lower order bit position. So to make sure that the character that we are considering in the first place goes to the corresponding place, we have to shift left. So by shifting left, we are going to have a 4 characters being kept in a right place. So once that is over, one more character of a given byte will be considered. That also will be taken using getC, the same process. When that comes, that will be stored in the accumulator. Now we have a higher order in the S register. We have a recent lower order data in the accumulator. So to add them to make it 1 byte, we will be adding register addition, which is a 1 by 1. So we'll get a 1 total byte. So complete 2 nibbles will be pushed together or combined together or integrated together to get a 1 byte data. This is the concept of a converting the character form into internal representation. So what we have done so far here is we have taken 1 character of a particular byte. We have combined that with another character so that we'll get a 1 complete byte data of an object program or object code is considered. Like that, we might be having thousands of bytes of data in the object program. For every pair of characters, this process gets repeated. Once that is done, we have to go to the next position. So our position is initially is 80. Now I will go to the next position. So 0, X, that is I am going to load from accumulator to my position, that is 80. Next I will increment TIXR. You know what is TIXR? We'll increment and we'll compare. We also seen it is X, X, because operating system should not have any boundary. It should be loaded freely. So it compares with itself. So nothing to worry. And second jump also, it is a straight jump. There is no conditional jump. So we'll go to the loop, meaning that we'll keep on doing this exercise until the entire object program of the operating system is loaded into the memory. Now the second part here is how to get the character. So second part here is to get the character. To get the character, we are using SIC kind of instructions here, where we have a TD, RD, WD. So here we require only TD and RD. Test the device, which is the device input. It is given that we are having data of operating system at the file, at the device called as a F1. So that is the reason why we have considered it as a F1 device, because X means device. Now we know that how to wait for this and get the data. Once the device is free, we'll get the data. So while taking the data, we have to keep 3 things in mind. One, whether we have reached the end of the object program, or are we taking the 0 to 9, the characters which are part of our object program, or are we taking the A to F, which are the other characters part of the object program. Apart from this, you should not be getting anything else in the program. If you observe the object program, header record, text record, E record. Header record is not required because it is a operating system. Even E record is not required here. Only the end of the object program is sufficient for this. So whatever you see in the text record, this is a complete object program. It should be either 0 to 9 or A to F. So only those characters are allowed here, and that's what we have assumed as well. No special characters are part of. If at all there are any special characters, we are going to ignore them. We are not interested in them. So first we are comparing with 4. 4 means end of text, whether we have reached the end of the program. If you have reached end of the program, that means entire operating system is already copied. Now only we are left with the executing the operating system. So to execute operating system, we should go to the location. What is the location? 80. So if you already reached the end of the program, next job will be to execute the program. For that purpose, we go back to the 80. This is 80 address. See, if you remember, 80 is direct address, no? That's why it is given as a straight way. So 80. Now, if it is not, that means we have not reached the end of the whatever the number we have. Next, we'll compare. Again, here compare 48 is given. 48 is a decimal. If you convert, it will be 30. So I have given yesterday 30 itself directly to avoid the confusion. So compare with the 30. When you compare with the 30, meaning that any character that is less than 30 as hexadecimal ASCII character is a waste character for us, except number 4. So number 4 we have already taken care. Remaining characters we should not be considering, thereby we ignore them. How are we ignoring that? Even if you see any character of that, no action has been taken here. That means we are ignoring all the special characters which are other than 0 to 9 and A to F, because object program contains only these 16 characters. Okay, if it is less than whatever it is, means you don't have a proper character, then there is no point in processing that. We'll go back to get another character. So we keep getting the character. Suppose the character whatever received is not end of file, is not a special character, then it should be either 0 to 9 or A to F. If it is 0 to 9, how to know that? So we subtract from 30. Again, it is not 48, we have taken 30. Why you are subtracting? Because up to 30, it is a waste characters. If you subtract something from 30, assume we have got 5 as my character. So 5 will be 35. 35 minus 30, I will get 5. So that subtraction will give me the actual value. I'll compare that with 10. Why you are comparing that with 10? So I may get any character, because after 30, we have characters up to 100. If that is the case, I may get some 50 characters. So whatever the characters I get, which is not in our range of 0 to 9, A to F, we should be ignoring that. So the subtraction value should be from 30 to 40. If it is between that, I will take it as a proper value. Otherwise, again, it is going to be an erroneous value. So if it is between that, we'll take that and we'll go back to our main program, so that the conversion from the character to internal representation takes place. But that is not end, no. We are also left with the A to F. So for that purpose, we are subtracting 7. We have seen yesterday why this 7 is. Not that A, B, C, D, E, F are 6 in number or some number. The 7 is because the difference between 9, the decimal number, and capital A, there are 7 more special characters, and those special characters also need to be ignored. For that purpose, we are doing this. So by doing all this, we'll get our data ready. Any other character, we are not writing the program. Any other character apart from this, we are just ignoring them. We are not doing anything. Meaning that we end up writing this program only to consider either end of program, that is a EOF or EOT, 0 to 9, A to F. Any other character is not going to be considered. This is the idea behind the SICXE object program, so that we can have a bootstrap loader. So hope it is clear now. Any doubts still about bootstrap loader? It's very important. You should know this. Any doubts still? Fine. If you don't have doubts, we'll move to the next concept, which is going to be our machine dependent features of loaders. We'll see 3 features here now. If you remember, in assembler, we have taken 2 features. One is the program relocation and generation of a object program, along with the data structures and the algorithm. In the same way, today we'll have 3 concepts of loaders which are mission dependent. One is the program relocation, as you have seen in the assembler, but the name remains same, but the process what we are going to incorporate is from the loader perspective. What you have seen earlier was a assembler perspective, because relocation is one of the functionality. If you remember, we have 4 functionality for a loader: memory allocation, linking, relocation, and program execution. So all, program loading into the correct memory. So if that is the case, relocation is one of the functionality. Of course, this is a mission dependent feature of a loader. So we'll discuss again relocation, but not from assembler point of view, but from a loader perspective. Next, we have a linking, because linking is also one of the assemblers, or one of the loader functionality, and this also precisely is a mission dependent feature. We'll also see how linking is going to take place. So more precisely similar to the control sections what you have seen in the assembler, in the same concept we look from the linking perspective, but it is a loader idea. Next, we have an algorithm, of course, like what you have seen for algorithm for assembler. We also encounter an algorithm for both pass 1 and pass 2 as far as the loader is concerned. These are the three things what we will discuss. Probably today we can complete the first one, that is a relocation with respect to mission dependent feature of a loader. Okay. Now, so before we discuss about mission dependent loader features, which is a program relocation here. So program relocation we are going to discuss in detail, but remember it is from a loader point of view. That is the caution. So let us recall what is the program relocation quickly, what you have seen as far as the assembler is concerned. So from the assembler perspective, program relocation is a concept that facilitates the assembler at the time of assembling the program, that there is an instruction which is beyond the limit of the address field of a given architecture. Thereby, that address has to be considered whenever there is a need for the program relocation. So assembler is only going to caution the loader that, look, there is an instruction which is going to be taken into consideration, or which need to be taken into consideration rather at the time of a program relocation. So meaning that the instruction that is assembled at that point of time when assembly is being done, it was not considered to load anything. It is only assuming that the program is going to be loaded elsewhere. So at the time of assembly, it is only a notional way of identifying that there is some set of instructions, or one instruction for that matter, depending upon the program, that these instructions may require some additional exercise or additional treatment when they are considered for the execution. But how do the system knows? That means your loader or OS knows, unless assembler provides the mechanism. So that is the reason why program relocation was dealt at assembler level using the modification record, wherein assembler used to identify those instructions having format 4 type of instruction to inform the loader or the operating system in general that such instructions where modification record has been considered need to be looked into specially at the time of the program loading. Now we are into that particular concept. Now assembler has given the program, no doubt. Now we are at the concept of a loading. Assume that program requires a program relocation. So how does loader is going to do that is what the concern we are looking at. So we know that now a loader that is going to accomplish the process of relocation of the program for execution purpose is going to be called as a relocating loader. So because the purpose is same, the loader is going to relocate the entire program. So what do you mean by how does the loader is going to relocate? Do you have a separate loader for that? Definitely no. The same loader, but it is going to incur an overhead, meaning that like a program if else statement, if this is the case, do this, else do something else. So if it is absolute program, else is not required. If it is not absolute program, else part is required. Like that, the same loader is going to consider both. But only thing is, if at all a loader is designed such that it is capable of considering relocation also, then we call that as a relocating loaders. Because why we are talking about the word relocating? In the previous class, we have talked about absolute loader. If you look at the algorithm, there was no else part at all. It's only if. If it is so and so, take the program and load at the place wherever you want. So there is no else, isn't it? The same concept here. In relocating loader, you should have both. It should be accommodating both absolute as well as the relocation. Thereby, a loader which is capable of performing relocation also is going to be termed as a relocating loader. It is a loader, no doubt. So, but we are giving an adjective or additional name for it as a relocating loaders, because our functionality demands that a loader should know how to perform the relocation. So design of a loader. If tomorrow if somebody asks you to design a loader, what you should be doing now? You should consider all these 4. That means how to allocate the memory from main memory. Second, how to execute the program with linking when multiple programs are there, how to link them. Next, third one, if there is a need for a program relocation, how program relocation has to be considered. And last one, store the program into the loading purpose into the main memory for the execution point of view. All these four has to be considered by a designer. So tomorrow there might be an innovative question. So what are all the a designer of a loader should keep in mind while designing a loader? What they have to do? These four functionality. A designer should be considering this functionality and do the program design for a loader. So that's what the idea behind this. Now, hope it is clear now. So program relocation from assembler point of view is only like a signboard. It is telling that, look, tomorrow when this program is used for a program execution, it has to be loaded into the main memory. While loading, do this. For what? Wherever there is a modification record. It's only informing, but this is like a planning committee. Who is execution committee now? Loader is the executive committee. What it should do now? Okay, my boss has given me the direction. The assembler has told me that these are the instructions which I need to consider at the time of loading. So let me treat them properly. So loader is executive body here, which is going to make sure that the program is relocated properly, because that is actual work. Real work. If that is the case, loader should know the combination of the program which is involving the modification record. So now there are two methods which we can consider for the program relocation. One, obviously the modification record. The other one is the modification bit. So while doing modification record, it is same as what is given by assembler. The loader is not having any special modification record. It is going to make use of the modification record that is already provided by the assembler. So let us look at that. So modification record, we know that it is having column 1M, column 2 to 7, starting address of the record that is requiring relocation. We have discussed enough on this, why it is only called record, and we have seen what is address. We have to take all those. Then 8 to 9, the length of the record, which is normally in half bytes. We have also seen a extended or modified modification record in terms of a control section, which we had column 10 as a plus or minus, which is a modifier bit. Then 10 to 14 is the actual label that is going to be used for addition or subtraction. This is what we have seen with respect to the modification record. This modification record is sufficient for the loader to make use of the whatever the modification that is required, and corresponding modification is done. So this is not special. Whatever is given by the assembler, your loader is going to do. But the question here is there any better way to perform? Because loader job is what? Whatever assembler has given the object code, it has to load into the memory. So while doing so, let us consider a situation. So this modification record is pretty same, or rather it is same as what you have seen in the assembler. So loader is going to just use that and make sure that the program is loaded at the corresponding location. It's only real time. As I said, it is the executive authority or body which makes sure that the program is loaded at the location which is available at the time of loading. That's all, by making use of the modification record. So it makes smooth. Now question here is, or maybe scenario, consider an SIC program. Now forget about SIC-XC now. We have seen SIC-XC, how we can avoid the format 4 instructions, right? Format 4 instructions in the first program we have taken 5. Later it became 3, it became 2. How we did with that? We have used program blocks, we have used control sections, we have used our LTORGs, we have used so many concepts to avoid or reduce rather the format 4 instructions. We could succeed as well. Now the question comes with the SIC. If you look at the SIC, SIC has only one instruction format. There are also only two types of addressing modes. One is a direct, index. So index addressing mode is of no use for us. It is only for array type of thing. So next we are left with only direct addressing mode. So assume in the case of SIC, when your boundary is beyond, how to say, your base or PC relative, then we may end up having a multiple records or multiple instructions which are involving your format. I can't say format 4 because there is no format 4 in SIC. I can say an extended requirement of a addressing mode or instruction format. If that is the case, in SIC, if you write a program, let us say you're writing a program, what you have considered so far as SIC-XC, In SIC-XE itself, we have written a 40-line program. Assume the same program is supposed to be written in the SIC. How many instructions you can expect? Any guess? I have a program in SIC-XE with 40 instruction. I want to translate that program into SIC-XE. So what could be the length of the program? How many instructions you might have? Any guess? Any idea? We have seen RISC, CISC, We also seen programs. SIC we took 4 instruction, whereas in SIC-XE it took 3 instructions. So 25% reduction is there. So like that, I have a 40 instruction program in SIC-XE. Tomorrow, if somebody asks me to write that in SIC, how many instructions I may have in SIC equivalent to those 40 in SIC-XE? Just guess. Will it be 40 or more than 40? Hope you are there.
More than 40.
How many? 50? 60? 100? Just guess. We are not hidden program. Nobody is going to punish you if you say something. But I want you to whether you understood it or not. If you keep quiet, then I'll get a wrong impression that you know everything, which is not true. So you are so dull to even guess also. Pathetic. Okay, I'll leave it to you. So if you don't open mouth, I am helpless. Fine. Anyhow, we know the difference between RISC, CISC. So SIC-XE program, if it is a 40, obviously it will be something beyond double, maybe 60, 70, 80. It depends. So it is going to be a huge number of a huge program rather in SIC. So now assume the 5 instructions what you have used in SIC-XE with the extended format 4, probably they end up in 10 instructions. Like that, when I write a complex program or a bigger program in SIC, I may have more records. So more direct, of course, will be requiring this relocation. So every line in the SIC has to be relocated. So if you have a 100-line program, first of all, that itself is a huge number. A 40-line SIC program becomes 80, let us say. That 80 requires 80 more instructions. So every instruction in SIC, since it's a direct addressing, it needs to be relocated properly. So we may have, or we may end up having a double the size of the memory almost. So if I have 100 instruction, my object program may have 100 modification records in object program of SIC. Then it is going to be very, very, very cumbersome and tedious for the loader because it takes a lot of time. And even main memory, getting that space is very difficult. So we have another mechanism in terms of a relocation bit. This is actually original program what you have taken. We know that how it is being done. Now we have a other one called as a relocation bit. So relocation bit is the one which is going to be convenient for you. So this is what the program I was looking at. So look at this program. What type of program it is? Is it SIC program or SIC-XE program? What program it is? SIC or SIC-XE?
SIC, sir.
SIC. Anyhow, it is written there in the caption, nothing to worry. So SIC program, as we know, we have only 2 addressing modes. One is a direct, other one is a index. So this entire program, you will see index only at 2 places. At line number 160, which is having X, and line number 225, which is having X. Apart from this, you can see if you roughly count around, say there are 30 instructions. Out of 30, 2 are from the X. So 28 instructions are involving the direct address. How do you say it is involving direct address or not? Let me check. So RET ADR, you know how to assemble, no? RET ADR, what is address of RET ADR? 0033. So 0033 is directly used here. Let us take another one. So buffer. So what is buffer here? Buffer is having 0039. So 0039 is directly used. So this is an example of a direct address. This is what we have seen. That means out of these 30 instructions, 28 instructions are involving, let us say, direct address. Then you, for every instruction of direct address involvement, we should write a one modification record. So obviously, your program, which is having a 30 instructions, will be ended up with a 58 instruction, which is almost double. Why? Because we have used only direct address, because we are talking about a SIC mission. In SIC mission, we do not have a variety that we have in the SIC-XE. So we have to use only that program or that instruction which is available to complete the program, because we need to do something with this. So if that is the case, we don't have much flexibility. That means when loader is a loader, I can't have SIC loader separately, SIC-XE loader separately, because operating system has to control. If that is the case, so many loaders will be involving, may be difficult for us. So the loader, what is designed, should be capable enough to make sure that all varieties of programs will be able to be considered. That's why the design of a loader is not easy. But anyhow, we are working about SIC and SIC-XE loader. Let us confine our discussion to that only. But whatever it is, SIC-XE or SIC loader should be capable enough to do this. If you are designing an SIC loader and your loader program is going to be a very, tricky business, because it has to consider every modification record which may consume a lot of space. The solution for that is how easily or how methodically or how conveniently we can refer those modification record. For that purpose, we have got a concept of a relocation bit. So now relocation is mandatory, relocation is necessary, rather relocation is inevitable. If that is the case, we have to deal with that. We cannot say no. But while dealing that, how do we do it in a efficiently is what the question. One way is having the modification record like this. But this is a problematic. Now, what is a problematic? Because in a architecture like SIC, every instruction almost requires a modification record. If I have 100 instructions here, I may end up with having 100 modification records, which is going to be a bit complex program, and thereby dealing with those type of programs involving modification records becomes a Herculean task as far as the loader is concerned. So that is the reason why, is there a way where we can mitigate this or figure out this such that loader performs its job efficiently without wasting much memory. So solution, what we see in pipeline, is in terms of a relocation bit. What is relocation bit? Before we go to relocation bit, let me show the object program that is involving the relocation bit. So relocation bit is being used here. If you observe here, there is some change here in the T record. So far the T records were different. Now the T record is something having special data here. You'll observe that. So you see in this case, FFC is something new is added here. E00, something new is added here. Another FFC, something new is added here. 800, something new. This new, what is being added? Let me show the original text record. So this is the original text record. You don't see anything that after T, we know the starting address. After that, we have the length. Next, immediately object program. So T, starting address, length, object program. But look at this current text record. There is something different. T, starting address, length, then something else. Before object program, something else has come. This something else is going to be called as a bit mask. So bit mask is nothing but a group of characters, a group of bits rather, which are going to help the loader to identify how the relocation bit is going to be used. So what we have to see here is the need for relocation bit. Why it is required now? So it is required for those architectures which involve majorly direct addresses. If a program involves majorly direct addresses, the assembler has to almost double its effort and create modification record for every instruction that is going to involve the direct address. That is a headache at the assembler. Sorry, headache at the assembler level. Later, at the time of loading, while loading, so much of memory is wasted. You may not be getting memory. Just now we have seen memory of a RAM is very, very important. We cannot afford to waste. So you may end up in taking a lot of time to execute a program. So to avoid that, do we find any solution? Yes, there is a solution. What is the solution? The solution is in terms of a relocation bit. So that relocation bit can be, as the name says, bit. It is 0 or 1. If my instruction is requiring relocation, I say 1 is the relocation bit. If my instruction does not require relocation, then I say 0 is the relocation bit. Let me take an example. So what is example? FFC. Just now we have just observed that FFC is the one bit mask that we have used. So FFC, if you split into binary, F means 1, 1, 1, 1. Another F, 1, 1, 1, 1. Next C. C means 12. 1, 1, 0, 0. So understood what we are doing now? Each one is a bit, relocation bit. Each one is a relocation bit. So what are we informing the assembler or loader here? That there are 12 if you observe, and we know that in a given 10 to 69 maximum I can have a 10. So that's why we have given room for a 12. So no doubt these two will not be used. So 10 are accommodated. That is the reason why it is left with only FFC. Why not more than that? Because the room existing to load in a given text record is maximum 10 bytes. I mean 10 instruction. So we have given room for 12 because I cannot separately store 2 bits. It should be in group of 4. Thereby these two will be almost 0. So only these 8 bits are important for me. But I cannot, 10 bits. We cannot put 10 separately. So we have used 12 bits because in terms of 4, 4, 4, 4, 3 is 12. Now FFC here. FFC means 1, 1, 1, 1. Another F, 1, 1, 1, 1, 1, 1, 0, 0. What is the meaning now? The first object code. What is the first object code? This is the first object code. What is the second object code? This is the second object code. What is the third object code? This is the third object code. Which is the fourth object code? This is the fourth object code. Which is the fifth? It's like this. So 1 to 1. So for every object code combination, I have assigned 1 bit. When I have assigned 1 bit here, what is the meaning now? If there is 1 here, this particular object code need to be modified. Requires relocation. If this is we are going to modify that. If 0 is there, we are not going to modify. So am I audible now? Is internet is live? Are able to hear me?
Yes, sir.
So,
Because some internet, let me know if some, because I am at home, my internet may be not stable. Let me know if you are not getting. Okay. Now, when I have 1 here, corresponding to the object code, that corresponding object code is going to have a relocation, or it requires a relocation. If it is 0, I will just make it 0 just to understand. When I make it 0, this corresponding object code, that is 481039, does not require a modification, meaning that it is not an instruction involving a direct address. So wherever a direct address is there, we are going to treat them separately. Look at here. FF means all 10 instructions here require treatment. They need to be modified. Take another one. Somewhere it is written 800. What is 800? 800 means 1 1 sorry 1 0 0 0 0 0 0 0 0 0 0 0. In this, only one instruction requires relocation, all others are 0. That means this 1 is corresponding to this 0 is corresponding to this 0 is corresponding to this. So the out of these 3 instructions, only one requires relocation modification, remaining 2 does not. So what is the meaning of relocation bit here? If any instruction that requires modification, that corresponding bit in this bit mask is going to be 1. If any object instruction does not require modification, then that is going to be identified as a 0. So 1 0 1 0 concept. So when you group them together, we call it as a bit mask. So bit mask is like group of these bits. So I can take analogy. In Unix, we have seen umask. What is umask? Anybody recalls umask? What was the umask we have seen in Unix? What is umask? That was not discussed during lockdown. That was discussed in class, no? If something was discussed in lockdown, we may say we didn't attend, we could not get. But in class, we have discussed it in detail. And unfortunately, it was me who discussed with you. So what is umask?
User file creation.
User file creation. Okay. You can recall the number. What was the umask value default?
Sir, 0022.
0022. Okay. First 0 you can remove. It is 022 because 777555. No, it's only 3 characters, not 4 characters. 022. So umask is a 022. What is the masking there? Why I'm just giving relation. Why I'm calling a bit mask here? Masking means you mask. We are going to mask the user credentials there. What are user credentials? The permissions that we have given to umask. So when you create a file, in an ordinary file, it was 666 minus 022. At the end, you will be giving 644 as a permissions for the user. So umask value, that is 022, was used to mask certain values from the user perspective. Similarly, the same umask was given to the directory as a 777 minus 022, which was 755. So we are masking some information. So one is masking means we are not making it visible. It is oblique. So we are not giving that transparently. So that is not under the control of a user, but it is a control of a administrator. So masking business is nothing but grouping certain data, not making it so visible or transparent to the outside world. It is like a black box. Similarly here in the concept of a relocation bit, the mask is nothing but we are providing the data of a modification in terms of this group of characters. Here we are not telling FFC means 1011 or 1100. That is internal to the assembler and loader. If you open this, you don't see what is this. So one corresponding to 1212, one value or one bit to the first object code, second value to the second object code, and so on, that we are masking. That means we are not giving that explicit information here. So that is the concept of a masking. Masking means closing. Now we are using mask. Now we are closing our mouth. So that is we are covering something. If that is the case, covering some data without making it so visible or transparent is what we call it as a masking. So bit mask is not something different here. We are going to group those bits, one for the instruction that is requiring modification, 0 for the instruction that do not require the modification. These characters or these bits, if you group together, we are going to call them as a bit mask. That is the idea behind the relocation bit. So relocation bit is nothing but, this is just an example I took for you. You need not write the entire program. You can write like this. Just what is important for us is this. We're writing exam. You need not write everything, but write these concepts. That is important for us. Here probably can give an example. When I say FEC, what is F? 1111. E means 1110. C means 1100. Meaning that out of 10 instructions, because last two, let us not worry. Out of 10 instructions here, 9 instructions are requiring the modification. Only one instruction does not require the modification bit. These relocation bits are grouped together as a bit mask. So FEC is a bit mask, FE4 is a bit mask, but internally they have been called as a relocation bits because they correspond to one in the text record, so that the corresponding object program will be identified if it need to be modified or not at the time of a relocation. Since it is used for the purpose of relocation, this bit is called as a relocation bit. So that is the idea behind the relocation bit. It's very important from exam point of view. They might ask you, explain what is a relocation bit. So relocation bit is a part of our loader, which is a mission dependent feature. In that we have two. One is a program relocation, other one is a program linking. So program relocation is what we are looking at now. In program relocation has two parts. One is a modification record and modification bit or bit mask. In the exam they might ask you bit mask or modification record. Both are same. Sorry, modification bit. Both are same. So nothing to worry. Bit mask or a modification bit. So that relocation bit or modification bit is a 0 for the instruction which do not require the modification. It is 1 for the instruction that requires a modification. So all these instructions which are part of a text record are grouped together such that the bit mask is created. So depending upon the instruction that requires modification, 1 will write. That does not require modification, 0 will write. Like that we group in terms of 4. That grouping is going to be a masking concept, which is a bit mask concept. So using that, we are going to efficiently manage. Why bit mask is required? It is not going to do any change here. Modification is required. We are not going to avoid modification, but we are going to mitigate, or we can say we are going to handle the modification in a better way. In an efficient way is what it is. What is the efficient way here? Instead of having 100 instructions, I'm going to reduce it to same number of instructions without much headache by adding the bit mask. So my program size is going to in turn make a lot of time to process. So I'm going to save both memory as well as time with the bit mask or a modification bit. That is the idea of a program relocation with respect to loader. In the exam, if they ask, explain program relocation. So what you should be writing? With respect to loader. If it is a module 3, that is with respect to loader. If it is a module 2, it is with respect to the assembler. You should be very careful. If the question is asked in module 2, you should talk about assembler. If the same question is asked in module 3, you should be writing about the loader. In the exam, they might be specifically asking, might not be asking. But you should know, if it is a module 2, it pertains to the assembler. If it is a module 3, it pertains to the program relocation. You should have a clarity. So in program relocation with respect to loader, two things. One is a modification record, which is same as your assembler, no change. But to provide more flexibility in dealing with architectures that are having only direct addresses like SIC, we cannot go with the modification record. So better approach can be relocation bit or a modification bit. That modification bit internally is grouped together in the name of a bit mask, only to make sure that every instruction that requires a treatment of modification is properly accessed or properly notified to the loader. So loader can perform easy program relocation. So that is the concept of a program relocation with respect to the loader. So that is for the today. So if you have any doubts, you can let me know, or we can meet in the next class with respect to the program linking. So meanwhile, let me take the attendance. Asta?
Present, sir.
Abhinav?
Present, sir.
Aishwarya?
Present, sir.
Ambarish?
Yes, sir.
Anu?
Present, sir.
Arbaz, Arjun,
Present, sir.
Ashok,
Present, sir.
Vinita,
Present, sir.
Bhargavi,
Present, sir.
Bhavisha,
Present, sir.
Chaitra,
Present, sir.
Chatterjee.
Present, sir.
Where are you, Chatterjee? So much of
Yeah.
absent. You're not regular.
Okay, sir.
What? Okay. Any issue? Any problem?
No, sir. Actually, yesterday I was in class, sir.
No, I did for many days. I have put absent for you. I don't know whether you have answered or not, but this is what's the case. If you attended class, fine. But if you are not attended, it is difficult. Of course, attendance is also required, but attendance status is very less for you, as far as my attendance sheet is concerned.
No, sir. I attend the class.
Then why are you not answering attendance? That means whenever I call, you are not there in then. You are not live. But whatever it is, your attendance is less. Okay. Diksha.
Present, sir.
Deepika LG.
Present, sir.
Okay, 110. Deepika MB.
Present, sir.
Murali Krishna. Murali. Rangubai. Guria Kumari.
Present, sir.
Harshit.
Present, sir.
Junjar.
Present, sir.
Sir, Gangubai present, sir.
ನೀನು ತುಂಬಾ ಅಬ್ಸೆಂಟ್ ಇದೆ ಗಂಗುಬಾಯಿ. ನೀನು ಸರಿಯಾಗಿ ಅಟೆಂಡೆನ್ಸ್ ಹೇಳ್ತಾ ಇಲ್ಲ ನೀನು.
ಇಲ್ಲ ಸರ್.
ನೋಡು ನಿಂದು ಅಷ್ಟೇ.
ಇಲ್ಲ ಸರ್, ಅದು ಇಂಟರ್ನೆಟ್.
ಗೊತ್ತಾಯ್ತು, ಬಟ್ ಆಮೇಲೆ ಹೇಳ್ಬೇಕಲ್ಲ. ಇಫ್ ಯು ಪುಟ್ ಮಾರ್ಕ್ ಅಟೆಂಡೆನ್ಸ್ ಆಬ್ಸೆಂಟ್, ದೆನ್ ಯು ಆರ್ ಅಟ್ ಲಾಸ್. ನೋ. ಓಕೆ. ಜುಂಜಾರ್ ಪ್ರೆಸೆಂಟ್. ನೋ.
Yes, sir.
ಕಾವ್ಯ.
Present, sir.
ಕಿಶೋರ್.
Present, sir.
You also should be very regular, Kishore.
Sorry.
Lata.
Yes, sir.
Manisha.
Present, sir.
Manjunath.
Yes, sir.
Nayana.
Present, sir.
Nilanjan. Nishant.
Present, sir.
Pavitra.
Present, sir.
Maithili.
Present, sir.
Priyanka.
Present, sir.
Pawan Kumar. Akash.
Present, sir.
Rajeshwari.
Present, sir.
Rakesh.
Present, sir.
Ramya.
Present, sir.
Rashmi.
Sir, present, sir.
Ravishankar.
Yes, sir.
Rizwan.
Present, sir.
Vishal.
Present, sir.
Savita.
Yes, sir.
Shruti.
Present, sir.
Sneha.
Yes, sir.
Purti.
Present, sir.
Srinidhi.
Present, sir.
Srinivas.
Present, sir.
Sunil.
Present, sir.
Vaishnavi.
Present, sir.
Vinny.
Present, sir.
Yes. That's all from my end. So if you don't have doubts, we'll meet.
Present, sir.
Diksha. 1 second. Yeah, Diksha present.
Rajeshwari present. Sir, Rajeshwari present, sir.
Rajeshwari, ಕೊಟ್ಟಿದ್ದೆ. Yes. Done. Thank you.